Hey guys, today's lesson is about 3.3, graphs of derivatives. Okay, we're going to start with this quick warm-up. If I give you a function, f, and it looks like this, kind of messy, how do you find f prime of negative 7? Well, that just means the derivative at negative 7. But I don't have a function to differentiate. I can't do power rule, can't do any of that. So I need to think about it another way. Well, remember, derivative is slope. The derivative calculates the slope at any point. So if I want f prime of negative 7, look at negative 7 and look at the slope there. We might have to estimate it, but if it's a linear piece, we should be able to find the exact slope. And here's negative 7 back here. The function value is up at 1, but I don't care. I want the derivative at negative 7. So look at the slope. The slope of this line, you know how to find slope. We've been doing that for years. Find 2 points, and you can just count rise over run. Looks like it's down 3 over 1. Slope is negative 3. Since the slope is negative 3, the derivative equals negative 3 at negative 7. Let's do the same thing for another one. The derivative at negative 4. Here's negative 4. The function value is also up at 1, but I don't care. I want the derivative at negative 4. Derivative is slope. So let's see the slope from this point. Find another good point. There's another good one. Looks like it goes up 3 over 2. So the slope is 3/2. Therefore, the derivative at negative 4 is 3/2. And you could tell when it's positive and negative. Like the first one we did, it's red. The one in red is negative 3 because the function is decreasing. So, of course, the derivative will be negative. Now, in the pink one here, number 2, at negative 4, the function's increasing. So, of course, the derivative should be positive because derivative is slope. Okay, how about at 0? F prime of 0 means the derivative at 0. Here's 0. The function value exists up at 2. Don't care. What's the slope? Oh, that one's easy. It just goes down 1 over 1, so it's negative 1. The slope is negative 1. Therefore, the derivative is negative 1 at 0. And the next one, let's do this in blue. F prime of 5, the derivative at 5. Here's 5. X equals 5. The function value is up at 2 again. Don't care. Didn't ask. It wants the derivative. That's just the slope. So let's see. It looks like it goes from here to here. Or you could even go from here to here, whatever. However you slice it. It goes down 2 over 1. Negative 2 is the derivative. Because at x equals 5, the slope is negative 2 of that line. I can tell because it's a straight line. So therefore, the derivative is negative 2. Okay. Number 5, we're going to talk about next lesson. List of values where f is not differentiable. That means the derivative would not exist. I'm going to tell you right now, derivative doesn't exist at sharp corners or discontinuities. So it would be x equals, see, there's a sharp corner here, really sharp corner here, and here. That would be at negative 6 and negative 2. X equals negative 6, negative 2. And then there's a discontinuity, of course. There's a huge jump at x equals 3. But again, don't worry about that. We'll talk about that next lesson, okay, in the middle of the week. Good. Little warm-up for how derivative connects to the actual original function. Derivative is slope, is what you should remember. Okay, let's look at this. Because we could think of the derivative in terms of slope, we can get a good idea of what the graph of the derivative, f prime, looks like by estimating the slopes at various points along the graph of f. So if they give you the original graph, you should be able to give me a good sketch of the derivative graph. Okay? Let's do this. So this example is already done for you. Let's see. The homework tonight, and there's a couple of problems like this on the exam. I'm not going to give you the derivative graph. I'm just going to give you the graph of f. Let's see. Function f. This is the function f. Okay? This, f prime, is what you need to create. Or y prime, the slope. This example is already done for you, so we're going to go through it. I'm just going to pick a random point. Here, the first point right here. 0, 1. Great. That's the location. But what's the slope? Well, clearly, if we were to draw a tangent line, it's clearly increasing. So the slope is positive. Honestly, that's really all I care about. This one specifically looks like it says the slope is about 4 because it goes over 4 over 1. That's fine. All I care about is the slope positive? It is. So at 0, they put a dot up at 4. The derivative is 4 because the slope is 4. Okay? Now, through all these, erase this, through the rest of this graph, it looks like it's always positive, right? It's always increasing. It's slowing down. At B, they say the slope is equal to 1. So at some point, my slope is going to hit 1. My derivative graph will go down and hit 1. What's more important, though, is to look at C. At C, something special happens. C is the top of a hill, right? Top of a hill means the slope. If I were to draw a tangent line, that's a straight horizontal line. The slope is 0 because it's constant there. For a moment, the function is constant there. It's not going up or down. So that's probably the most important point. And in the future, this is how we're going to start. Look for where the slope is 0 first. That's right at 2. The slope is 0 at 2. So at 2, on the derivative graph, it crosses the x-axis. That's probably the most important thing right there. Okay? So when the slope is 0, it hits the graph of the derivative, hits the x-axis. And then after that, let's see. Now look, it turned around. Now it's decreasing. The slope is -1 at D, according to them. So and that's where? That's like at 3. So at 3, my derivative graph is down at -1. Again, I'm just estimating the slopes at random points and then graphing them on the derivative graph at those same x values. And it's still decreasing. It's still going down. And then here at E, it says the slope is also -1. Well, they found it for us. Thank you. So at E, that's like at 5, right? At 5 here on the derivative graph, the derivative exists at -1. And then again, the next important, really important point is F. F is the bottom of a valley, if you will, or the bottom of a cup. Well, if I were to draw a tangent line there, it would also be flat, which means the slope is 0. So that means the derivative, f prime equals 0, or y prime, whatever you want to call it, equals 0. And that's at 6. So at 6, over here, the derivative graph, it crosses the x-axis. And let's see, after that, the slope is increasing, positive, positive, positive. So the derivative will be positive, positive, positive after that. Okay? This one might seem a little confusing because they found exact slopes for a lot of these, which honestly we never do. Okay? This is one example. The ones after this should be a little bit more clear. So here, we are going to, when given the graph of a function, sketch the approximate graph of the derivative. So just know they are giving us the original function, and we need to graph the derivative. So how do you do that here? Well, I'm not going to find exact slopes like that other example. I'm just going to think about 3 things. Literally 3 things for now is all you have to worry about. First, when is the function flat? Meaning, when is there a maximum or minimum? Usually, it can be flat without being a max or min, but usually it's a max or min. When does it flatten out? Whenever that is, you immediately know that, okay, that means the derivative graph has got to hit the x-axis, meaning the derivative equals 0. F prime of x equals 0. Let's do that first. Let me use red. Okay. Let's look at this original function. This is f of x, not f prime of x. Tomorrow we'll talk about what happens when they give you the derivative. They're giving us the original. Let's see. The only slope that I want to first care about is when it's flat. It only flattens out one time. That's it here at 2, right? At 2, it's at the top of a hill. And if I were to make a tangent line there, look, that's flat. So the derivative here, f prime of x, would equal 0. And that, sometimes I draw an arrow down just to show everyone. That means at 2, 0 on the derivative graph, let me do that in purple. This is f prime of x, a derivative. At 2, the derivative equals 0, right? So 2, 0 is the derivative value. That's where it crosses the x-axis. Where f of x is flat, f prime of x hits the x-axis. Feel free to pause at any point, obviously, to write this down or to slow things down and try to figure out what I'm talking about. That's how I always want you to start. If they give you the original and they ask you to draw the derivative, first find out where the derivative is 0. That's always going to be where the original function is flat. Good. Now you just have to look at what's happening around it. Well, in front of that, what are all these slopes? All these slopes, are they positive or negative? Well, they all go upward when you read it left to right. The slope is always positive. So the derivative graph, let's see, when f of x is increasing, let me use a different highlighter. When f of x is increasing, meaning there's a positive slope, and that's what this is, all that is positive slope. It's increasing. When that happens, the derivative is above the x-axis, aka f prime of x is above 0. Okay, well, that's not so hard. Just as long as it's above 0. Here. Whoa, that's... all right, here we go. As long as it's above 0, the derivative. But then, of course, at 2, it's got to hit 0. That's why we have the dot there. That's what happens before x equals 2. The function is increasing. It's a positive slope, so all your values of the derivative better be above the x-axis. Now, how about, let's use blue. Now, what happens when f of x is decreasing? When there's a negative slope? Well, that'd be everything, look, after this. When you read it left to right, it's decreasing, it's going down. Right? All these slopes are negative. So then the derivative is going to be the graph of the derivative is below the x-axis, aka f prime of x is less than 0. So after 2, because we know it hit 0 at 2, after 2, there you go. It's all below the x-axis. That is all I need. And now you might be asking, Mr. K, hold up. How do you know it's a straight line? How do you know it wasn't like curvy? That's still above the x-axis. How do you know it's not curvy here? I'm going to show you how. The original function was was a quadratic. Right? You can tell it's a quadratic. It's a parabola. It opens down. What happens when you take the derivative of a quadratic? Let's just say, for example, I have negative x squared. I know this isn't negative x squared, but this is an example of a quadratic that opens down. What happens when we use power rule? Let's say this was y equals. What's the derivative of a quadratic? Well, let's use power rule. This is negative 2x to the 1. Negative 2x, that's a straight line. That's a linear, and it's decreasing. Therefore, the derivative of a quadratic is always a linear. That's always going to be the case. You can check it using the calculus algebra or the actual graphical calculus. And there's nothing special about the slope of this line right here, ladies and gentlemen. All I care about is that to the left of 2, it's all above the x-axis, and to the right of 2, it's all below it. Meaning, I could have also had my line do this. This would work as long as it goes through 2. 2 is the most important thing, because at 2, there's a horizontal asymptote, meaning the derivative is 0. The slope, you might have made your straight line like this. Any of these work. Not all of them, just draw one of them. Okay? I'm not trying to get an exact derivative graph. I just want you to approximate. Let's do the other one. Let's look at this. They're giving us a function. This is f of x. They want us to graph f prime of x. Okay? It's important to know that. The most important point is, where does my original function flatten out? In this case, it flattens out here. There's a minimum here. It's the bottom of a valley. So if it flattens out, that means the derivative, f prime of x, equals 0. It must, because derivative is slope. And the slope here, obviously, is a horizontal line at 0. So at 2 on the x-axis, my derivative graph hits the x-axis. Because of this, wherever f of x is flat, there might be a maximum in there, the derivative hits the x-axis, meaning the f prime of x equals 0. Good. Now let's look at the other things. When is f of x increasing? the derivative is above the x-axis. When it's decreasing, derivative is below the x-axis. Okay, I could do that. See here, this is obviously, read it from left to right. It's a negative slope. It's decreasing. So before it, all these values should be less than, under the x-axis. After this, the function climbs. It's increasing, increasing. Therefore, the derivative is positive, meaning above the x-axis. There you go. And again, I know it's linear because I'm going from a quadratic. If I'm taking the derivative, I'm going to end up with a linear. And I'll show you why algebraically right now. Let's say you have a positive, quadratic that opens up. Let's say you have y equals x squared. Again, I know this isn't the equation of this parabola, but it's the equation of a parabola that opens up. What's the derivative? Power rule says it's just 2x. Well, guess what? That's just a straight line that has a positive slope of 2. There you go. This is a straight line with a positive slope. Okay? So connecting function families through derivative as well. Okay, let's look at the next one. This is the last one we're going to do. Oof, okay, this is, first of all, if I'm looking at the future, this is a cubic. Let's see what happens when I take the derivative of a cubic. For instance, if I have y equals, I don't know, x to the third, that's cubic. We'll get there. Like I said, the most important points are wherever the original function flattens out. Well, there's two cases here. It flattens out here. That's at -2. So I'll put a dot for the derivative. This is f of x. This is f prime of x, the derivative graph. There's a dot, it crosses the x-axis at -2. And look, weird, right here, there's another leveling off. There's a minimum. That doesn't happen at a perfect x value, but it happens at like 1.2 is my guess, whatever. Maybe 1.3. So at 1.3, I put a dot on my x-axis for the derivative. See that? My original function crosses the x-axis here, here, and here, but the derivative does not care. The biggest mistake is that people see that, oh, if it crosses the x-axis here, the derivative must cross too. No. The derivative only crosses the x-axis when the derivative equals 0, which would be these flat areas, the horizontal tangents. Okay, but now we have a good skeleton of a derivative graph. Let's see what's going on in between all these values. Let's see. Before the -2, always read it from left to right. Look, it's increasing. It's clearly increasing going up. What does that mean? F of x increasing means derivative is above the x-axis. Cool. It's all above the x-axis. Excellent. That's it. Again, I don't know the exact angle that it is, but as long as these values are above the x-axis. How about after the -2? Decreasing, decreasing. It's like a roller coaster. After it levels off, instead of going up, now it's going down, 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 all the way until the next leveling off. So that means the derivative, if the original function is decreasing, the derivative is below the x-axis. But remember, it goes back to 0, so it's got to come back to 0 at some point. So it's below the x-axis, but at some point it comes back up to 0. It must, because it levels off again at 1.2 or 1.3. Now what happens after 1.3? Well, this function's going up, up, increasing again. Man, it's quite a roller coaster, increasing again. So therefore, when it's increasing, the derivative is above the x-axis. Again, so there you go. That is it. That's my basic sketch. Now, yours might not look exactly like it. You might have something that looks like this. Don't draw them all. You might have something that looks like this, really shallow. It doesn't matter to me. They're all correct. All I care about is you show me the derivatives, when the derivatives are 0. And, of course, you can't make a parabola. Don't make it open downward, because that will be backwards. That will be if the original function was decreasing first, then increasing, then decreasing. But this one isn't. But as we see the cubic, when you take a derivative, it leads to, this is a parabola. It's quadratic. Why? Well, let's check. Here's an example of a cubic. What's the y prime? Power rule says 3x squared. Easy derivative. And look, that's a quadratic that opens upward. That's exactly what the derivative graph was. Okay, so it's all connected. You're not trying to be exact. My answers aren't exact. I promise you that. A sketch is what you're looking for. These three things are what will be checked. Okay? Tomorrow we'll talk about, we'll talk more about what happens when they give you a function. We'll talk about what happens if they give you the derivative graph, not the original. And then we'll talk about horizontal tangent lines. But that will be tomorrow. So for now, try the homework, part 1, and get it done. If there's any questions, I'll be in Zoom. Send your questions my way.